Now, because we are talking about the phase, means what is that instant when particle is completing its revolution and reaching inside the RF cavity. Means we are interested in the path length, because path length will decide how much time is taking in complete revolution. So how much path length is changed due to change in momentum when we compared with the synchronous particle, we will compute it. Now suppose this is a part of the curved trajectory. Curved trajectory means a trajectory decided by the dipole magnet, and this red curve shows the design trajectory. This bending is delta theta, and radius of curvature for the design trajectory is r naught. Now suppose some another particle which is having some momentum deviation from the design momentum will follow another trajectory due to dispersion. We already know that if particle is deviated in momentum, dipole magnet will send it to the other trajectory decided by the dispersion. So this is such kind of trajectory. So length of design trajectory inside the magnet is delta s, and length of the trajectory of particle which has some momentum deviation is delta s1. Now we will see how delta s1 is compared to delta s. So we can write down delta s very easily, r naught delta theta, and similarly delta s1 is equal to r delta theta. Instead of r0, it will have some r because momentum has been changed. Now r is basically in transverse coordinate system. You can see that here origin is when the synchronous particle is here, and this is the z or s you can say, and this is the x. So r will be x plus r0. So we have written down r0 plus x delta. So using these two equations, we can get delta s1 minus delta s, means how large is the path length compared to synchronous path of this momentum deviated particle, and this will be x delta theta. Now this x, it is decided by the dispersion. So in the place of x, we can write down d into delta. D is the dispersion at that location. So this delta s1 minus delta s, that is the change in path length compared to the synchronous particle, is d delta upon r0 delta s. D is the dispersion. So dispersion or bending magnet actually comes into the picture when we want to calculate how much path is changed. And this changed path actually causes the change in revolution time. Means dispersion plays an important role in longitudinal dynamics also. So this delta s minus delta s1 was calculated for a small segment of bending magnet. Now all over the ring, if you want to calculate delta L, it will be the integration of d delta r naught ds. Now over a one turn, means particle is exiting the RF cavity, and after one complete turn it is again reaching to RF cavity. In between these travel, delta remains constant, or you can say we are talking about a particular delta, and for particular delta, this we can define delta L by L for a unit fractional change of momentum. What will be the path length change, fractional path length change for a fractional momentum offset? This parameter in accelerator is known as momentum compaction factor, and it is just integration which we have written down here divided by L, because we have fractional change in the length. So this alpha actually decides what will be the change in revolution time for the particle which has deviation in the momentum. So we calculate that how much revolution time is changed. T revolution is given by L by beta C. So delta T by T, this is logarithmic derivative of the above equation, will be delta L by L minus delta B by C. This C will not be differentiated. It is constant quantity speed of the light. This beta C means we are talking about velocity. So this beta C is V. This beta is relativistic factor, beta. So delta T by T will be delta L by L, delta beta by beta. Means as momentum changes, we have calculated what will be the change in the path length, and as momentum changes, speed may also change. So this is the change in the speed. Now as particle travels at higher momentum, bending magnet bends less, so it will traverse a larger orbit, means path length will increase. So it will increase the revolution time. At the same time, because of the higher momentum, its speed may be higher, and because of the higher speed, its revolution time will decrease. So these are two counter phenomena which counters each other. One factor increases the revolution time, other decreases the revolution time. So by combining these two with opposite sign will give you the revolution time. Because we are interested in calculating the revolution time for the fractional momentum offset, so divide this complete equation by the fractional momentum offset. We have did this. Now this quantity you already know is alpha, momentum compaction factor. And this quantity in accelerator is given a new name, named either phase slip factor or frequency slip factor. So this is eta, which is the frequency slip factor. This is alpha, and delta beta by beta upon delta p by p means you can say delta beta upon beta is equal to, upon delta p by p. It will just 1 upon gamma square. This is an exercise for you to prove this relation. This is very easily how you can prove it. Just take beta or momentum in terms of beta and write down that. Means P is equal to beta C gamma. This is the momentum in terms of beta gamma. Now you can write down gamma also in terms of beta. Gamma is equal to 1 upon under root 1 minus beta square. So this whole equation will be in terms of P and beta. Now you can calculate delta beta by beta and delta P by P taking logarithmic derivative of this. So this is an exercise to prove this relation from this. In some literature, instead of delta T by T, they use delta F by F. Means instead of fractional revolution time change, they say change in fractional change in revolution frequency. Then the sign of the equation will be reversed. Means in that case, phase slip factor will be 1 by gamma square minus alpha. So in literature, you will see both kind of things. Some literature says frequency slip factor as alpha minus 1 by gamma square, and in some literature it is mentioned as 1 by gamma square minus alpha, because of the basic difference in the definition, whether we are taking the revolution time or revolution frequency. As we have delta T by T is delta L by L, delta beta by beta. So at one place, because this factor increases the revolution time and this factor decreases the revolution time. So at one point, this may occur, or one energy or one beta, this can occur that both component cancels each other. Means delta T revolution upon T revolution becomes 0. This is known as transition energy. Now you can see here, if delta L by L factor is large than the delta beta by beta, then frequency slip factor will be positive. When delta L by L will be larger than the delta beta by beta. Means delta beta is very small. Delta beta is very small means we are changing the energy but beta is not changing. It is the case of highly relativistic particles. So in high energy machines, generally frequency slip factor is positive. If this effect is much more than this, then frequency slip factor becomes negative. When it will be negative, it will be in low energy region. So low energy machines can have negative frequency slip factor. For an example, when we say that 800 MeV proton synchrotron or 1 GeV proton synchrotron, it means kinetic energy is 1 GeV and it is comparable to the rest energy of the protons. So in this case, we can say that we are operating the machine in low energy region. In this region, the frequency slip factor may be negative. But when we talk about say 1 GeV or 2 GeV of electrons, electrons have rest mass energy of 0.5 MeV. Means 1 GeV or 2 GeV for the electrons is a very high energy. This is much higher, means 1 GeV means 2000 times the rest energy of the electron. So in this case, this factor will be insignificant and frequency slip factor will be positive. So in general, all the synchrotrons, electron synchrotrons have positive frequency slip factor, while proton synchrotron may have positive or negative frequency slip factors. And when then these factors cancels each other, this is the delta T revolution upon T revolution becomes 0. That energy, that particular gamma, when this occurs, is known as transition energy, and that gamma on which this occurs is known as gamma transition. So gamma transition is 1 upon root alpha. Now the thing is that if machine is operating on gamma transition, then revolution time becomes independent of the momentum. Means whatever is the momentum, even a momentum particle deviated in momentum has the same revolution time as the on momentum particle. This is the isochronous mode of the machine. Cyclotron operates in this mode. In cyclotron, revolution time doesn't depend on the momentum. Synchrotron can operate in all the three modes. Means it can operate in the synchronous mode as well as frequency slip factor plus means above gamma transition, and frequency slip factor minus means below gamma transition. Now these, while we are talking about these, because higher momentum particle in this case when delta beta beta is larger, means frequency slip factor is negative. Negative means when we have higher momentum particle, it takes shorter time and vice versa. Now we see what is the effect of this gamma transition on the longitudinal dynamics. This is the RF wave inside the cavity, and suppose particle arrives in the RF cavity at this place. These are the initial condition for 3 particles. The particle in between is the synchronous one. Means it will come again on the synchronous phase. We are assuming that synchronous phase is not changing, so this particle will come again in the next term in the RF cavity on the same phase here. Now suppose this machine is operating below transition. Below transition means higher momentum particle takes a smaller time to complete it. Higher momentum particle is faster. So this particle gets more energy than the synchronous one, because this is in higher field, this is feeling higher field than the synchronous particle. Then it gets more energy. So it is at higher energy than the synchronous one. Because of the higher energy, its revolution time will decrease and it will reach earlier than this point. Means this particle will come here instead of here. And similarly, this particle is at lower energy, so it will take longer time to complete the turn. So it will come here. Means these particles are coming towards the synchronous particle. In next turn, still it is at higher potential. Means in second turn also, it is gaining more energy than the synchronous one. Although the rate of change in energy has been decreased, but still it is at higher energy. So in next turn, synchronous particle will arrive at the same phase, while this particle will be more closer to synchronous phase, and this particle will also be more closer to synchronous phase. In next turn, this will be more closer, and subsequently the phases will change its sign with respect to synchronous particle. Means red particle will then have minus sign with delta phi, and this particle will reach here and this particle will reach here, and then this will be repeated. Means some type of oscillations around synchronous phase is taking place. This is known as phase focusing. As quadrupole focuses the beam and excites the betatron oscillations, similarly RF cavity also focuses in longitudinal dynamics, longitudinal direction, and it also excites a kind of oscillations known as synchrotron oscillations. These are synchrotron oscillations. Now we take another three initial conditions. This time we are taking on this one. Means this was on rising edge of the RF field and this is on the falling edge of the RF field. Still, synchronous particle is taking the same energy as of the previous case. So it will come again on the same phase after first revolution. However, because a higher energy particle, means red particle, will come early, so it will go away from the synchronous phase. And similarly is the case for the lower energy particle. And this gap will increase subsequently turn by turn. So this gap has been increased. Means it is a defocusing phenomenon and motion is not stable. So we have seen that if machine is operating below transition, then rising edge of the RF provides a stable motion while the falling edge provides an unstable oscillations. So we will, all the bunches, all the particles will concentrate towards this. If machine is operating above transition, then this falling edge will provide the stable oscillations while this rising edge will provide a defocusing phenomenon, means unstable motion. Now we derive this equation of motion. Means we have seen the qualitatively that if a particle is deviated in phase or energy, it will execute some kind of oscillations. Now we will derive quantitatively that what is kind of that oscillations. So in one turn, this, keep in mind, this delta phi is basically the change in phase with respect to synchronous particle. Means we can understand it like this. Suppose a particle in n plus 1th turn has the phase with nth turn plus omega RF t revolution. This is the phase in the n plus 1th turn for a particle. Now similar equation will hold for the synchronous particle also. So we will have phi of the synchronous n plus 1th turn is equal to phi of the synchronous in n plus 1 plus omega RF, and in place of t revolution it will be t revolution for the synchronous particle. Now in place of t revolution of asynchronous particle, we can write down it as t revolution of the synchronous particle plus some delta t. So what will be the delta phi in the n plus 1 term is equal to delta phi in the nth term plus difference of these. So this will be omega RF delta t. This is the difference of these two equations. So this is the deviation of the particle with synchronous in the n plus 1th term. This is deviation of the particle from the synchronous phase in nth term, and this is omega RF delta t. And at the place of delta t, we can write down t eta delta p by p with the definition of the frequency slip factor. This is frequency slip factor. Frequency slip factor was defined as delta t by t upon delta p by p. So delta t by t will be eta delta p by p. So delta t will be equal to eta t delta p by p. So this is written here. Now we can see that delta phi n plus 1 minus delta phi n is equal to this number, and this is change in the deviation of phase in one term. That's why it is written d delta phi over dn. dn means in one term. We are counting with terms. So this is the change in phase deviation in one term, phase deviation with respect to synchronous one, and it will be given by omega RF t revolution eta delta p by p. Now omega and t revolution, we have seen that t revolution should be equal to HTRF. It should be an integer multiple because t revolution is the here, t revolution is for the synchronous particle. So t revolution is the HTRF, and we want to change this delta p by p in terms of delta e by e, because when the particle traverses through the cavity, it is easier to calculate the delta e by e. So instead of delta p by p, we are writing delta e by e. So delta p by p is equal to 1 by beta square delta e by e. Again, this is left as an exercise to prove this delta p by p should be equal to 1 by beta square delta e by e. This is an exercise for all of you. So in place of delta p by p, we have written down this delta 1 by beta square delta e by e, and when we take t revolution as HTRF, so we have omega RF t revolution is equal to omega RF HTRF, and omega RF TRF will be 2 pi, so this quantity will become 2 pi h, and this 2 pi h is written here. So this will be 2 pi h eta upon beta square delta e by e. As we have calculated the change in phase deviation with respect to each term, we also calculate what is the change in the energy deviation in one term, following the similar path. So in the n plus 1th term, synchronous particle has the energy as nth turn energy plus qv sin phi s. Phi s is the synchronous phase. Similarly, for the asynchronous particle, means a particle which is not synchronous, which is deviated in the energy or phase, it will have energy in the n plus 1th term is equal to energy in the nth term plus qv sin phi s plus delta phi. This delta phi is the phase deviation which is here. So if we subtract first equation with the second, then we will have again here similarly what is the change in energy deviation per turn, and this will be qv sin phi s plus sin phi s. Here we have delta E by E, and here we get delta E by delta N. So d by dn of delta E. So if we differentiate this equation again, we will get d by dn of delta E, and then this value can be put into this equation. So let us differentiate this equation again of the phase equation. We will get, this is a simple differentiation, so you will get this equation. Now use this relation in the last equation. So you get complete equation in the phase. This equation contains only phase deviation. This is the phase deviation and this is the phase deviation. Now this equation looks complicated, but you can understand it very easily. How? Suppose deviation in phase is not large, means this delta phi is very small quantity, and if delta phi is very small quantity, this expression sin c plus d can be written as cos c plus d by 2 sin c minus d by 2, means sin delta phi by 2 term will be there, and because delta phi is small, you can use relation sin delta phi by 2 is approximately delta phi by 2, and cos phi plus delta phi plus phi upon 2 will be cos phi s. So this will be cos phi s, and this delta phi is due to sin delta phi. Now you can see that this equation is similar to simple harmonic oscillator equation. This is d2 phi tan square, this is omega square, and this is again delta phi. And this is synchrotron oscillations. Now you can see here, this overall number should be negative for oscillations because it is an RHS, so it should be negative for the oscillation. Now here two quantities can be either positive or negative. One is the frequency slip factor and other one is the cos phi s. So if eta is plus, then cos phi s should be negative, and if eta is negative, then cos phi s should be positive. Only then this will represent a simple harmonic oscillator. Otherwise exponentially growing solution will be there, means not bounded motion. Now you can check, which we have seen earlier, that in the below transition phi s should be in the rising edge, and for the above transition phi s should be on the falling edge of the RF field. Because this is now a simple harmonic oscillator equation, we can get ellipse similar to the transverse plane in the delta phi and delta e plane. So what kind of ellipse we get? Here we draw the delta phi, and here we draw the delta e. So at this location we have delta phi also 0 and delta e also 0, means this is the synchronous particles position. The origin shows the synchronous energy and synchronous phase. Now for small oscillations, as suppose this is the phase deviation initially particles with respect to synchronous one, as turn by turn this phase deviation diminishes, means it comes simply. However, the energy deviation increases because up to certain point it gets more and more energy than the synchronous one, so it will come here. After this, when particle crosses the phase of the synchronous particle, its gap in the energy with the synchronous one will reduce, and it will come here, and again it will come. So this is a kind of ellipse we get in the longitudinal plane. This shows the simple harmonic oscillations. However, you can see that if delta phi is large, the equation is no longer linear. It is a non-linear equation if delta phi is large. So it means if delta phi is large, this ellipse will be distorted, and this will be like this. Ellipse will be distorted like this. Even if we make delta phi large, it will distort more, and like this. And if delta d beta by dt is 0, means if we are talking about the storage mode of the operation, then this stable phase will be 0 to pi and minus pi. So above this, if suppose phase is here or energy deviation is here, what happened to this coordinates? So this coordinate will have open trajectories. no bounded motion like this. So you can see that inside this area there is a stable oscillations, and above this area there is no stable oscillation. So this area is known as RF bucket. And the curve which separates stable and unstable zone, this is the curve which separates. This is known as separatrix. If dB by dt is non-zero, means we are boosting the energy. In this case, shape of the RF bucket changes and it becomes like this. Delta E, delta phi, and this is the phi s, so like this. This is even more distorted, and now it doesn't span up to the 2 pi area. Instead, area has been shrunken. As phi s increases, area of the RF bucket becomes smaller and smaller. So this, if particles are inside this RF bucket, it will exhibit stable synchrotron oscillation, and outside the bucket will be lost. So it is similarly, as we have certain acceptance in the transverse plane, and if beam is within that acceptance, it will exhibit betatron oscillations. Otherwise, the particles will be lost. So same kind of thing is also here. So in nutshell, we can see that when particle is exhibiting motion in a synchrotron, it exhibit 3 kind of oscillations. One is horizontal betatron oscillations, another is vertical betatron oscillations, and third one is the synchrotron oscillation. And like the betatron tune, we can also define a synchrotron tune. Synchrotron tune means number of synchrotron oscillations in one turn. Now you have seen that synchrotron oscillations are slow, means in one turn even a fraction of the oscillation completes. So synchrotron tune will also always be lesser than 1, and betatron is much higher than 1. In one complete turn, many betatron oscillations takes place, while in many turns, one synchrotron oscillation takes place. So synchrotron oscillations are very slow oscillations compared to betatron motion. We have studied these motion in decoupled way, means horizontal betatron motion is not coupled with the vertical motion, and synchrotron motion is not coupled with the betatron motion. In real practice, these all the oscillations are coupled to each other, and there is a rich dynamics which arises due to coupling, and many type of resonances occurs. So this kind of studies are followed in the accelerator physics for designing an accelerator. So again, these basic references covers all the things which I have shown here. And in next lecture, we will study about a special type of accelerator, synchrotron, which is known as synchrotron radiation source.